Hello everyone, today we're going to be doing exam 3 for transport 2 and we're going to start off with part A. So in part A, the situation that we have is we have a thermometer wrapped with a wet cloth that is taken and being swung around. And what we do is we can actually take the temperature while it's being swung around, and that is called the wet bulb temperature. Now with that, we're later on also going to be comparing to the adiabatic saturation temperature and so on and so forth. But for now, we're going to start with part 1. Part 1 of our problem, we're trying to find the Lewis relation. So to start us off with that, we're going to want to compare the mass flux and the heat flux. So first we're going to write those two equations out. We know that the heat flux is equal to that heat transfer coefficient times that temperature from the surface to the temperature away from the surface. And what I'm talking about this is if you look at while it's being spun around, the cloth, or the thermometer with the cloth while it's being spun around, the temperature at the surface is different from the temperature away from the surface at any point really, but we're saying infinity, away from the surface. That temperature is changed due to the evaporation of the water. It changes the temperature in the air. There's a different humidity level at each point away from that wet cloth thermometer, the wet bulb temperature. For the mass flux, we already know this one. We've worked with this before. We take that mass transfer coefficient, but we're also going to be looking at the concentrations between those same 2 points. And the concentrations, I'm talking about concentration of water in the air, the humidity going through. So with that, I'm going to go ahead and block this off right here. Now with that, we're going to want to find ways to compare these two. And a way we can do that is we're going to first start off by looking at the Sherwood number. And we talked about this in the last equation. We know that the Sherwood number is equal to, in this sense, that mass transfer coefficient times a distance over that concentration coefficient. So with that, we can actually compare that to this because there is another number that works with that, and it just changes these two values here, not that distance. And it's called I'm going to botch the name of it, the Musil number. I'm trying too hard on it. And that takes that heat transfer coefficient times that distance over, and instead of that concentration coefficient, we're going to be working with the heat coefficient there. And so with that, we're actually going to want to look at equations for this. Because in the last problem, we worked on the equation with the Sherwood number. We remembered that, and by last problem I mean for exam 2, of course, we know that the Sherwood number can be written as A times the Reynolds number to the power of B times the Schmidt number to the power of C. And what A, B, and C are, those are just experimental data points. We discussed that in exam 2. If you would like to go back, you can see how this problem works out. So those can be any numbers that we want here, okay? I can make A equal 0.5, I can make B equal 0.2, C equal 0.005, whatever. It doesn't matter here. So I'm going to leave those as equations, but generally you can input any data points there, and the reason why being is because we're talking about the comparison with that Musil number, and we can actually rewrite this here in the same way. So that Musil number is also A times that Reynolds number to the power of B, but instead of that Schmidt number, we're actually going to be working with the Prindle number. And I'm going to write out what these are. So the Schmidt number is that viscosity over the density times that concentration coefficient, and the Prindle number, this isn't a minus, this is an arrow so that you know we're not subtracting those, is that viscosity times the density, and we're going to be doing that by that heat coefficient there, that heat transfer coefficient. So with that in mind, we're going to be using this in a second, but what we can actually do is now we're going to take these, and I know I wrote it a little bit differently actually, But we're going to be taking these and we're actually going to have the Musil number over the Sherwood number. And the reason why being is we're going to be able to take some of these values and cancel it out. And what helps with us that here too is this is actually equal to 1 over the Lewis number. And I'm writing it like this, it's just easier for me. You can write Sherwood over the Musil. You can write it like this, and that'll equal the Lewis number. You can work with it any way. I'm just writing it like this myself. So, from that, what we need to know is that we still have a lot of variables we're working with, and we're going to plug and chug all this in a second, but we're going to first focus on that Lewis number. Because we're working with water vapor, water temperatures and all that, we can actually take that Lewis number and we can assume that it is roughly equal to 1. And we're actually going to go ahead and plug that 1 in there because it'll help us solve this equation. So I'm going to rewrite this as equal to 1. Now with that in mind, I'm going to go ahead and rewrite this Musil and Sherwood because, again, we have the numbers right here. So we know that is H, that heat transfer coefficient, times that distance over that heat transfer, and then that mass transfer coefficient times that distance over the diffusivity coefficient. And with that, we can already get rid of our first value. Distance goes away, so now we have less to work with. But also from that, we can also tell that since this was that Musil over the Sherwood, and we were able to take these two numbers and cancel this stuff out, because they're all divided by each other, so they'll end up canceling out. All that's left is that Prindle and Sherwood to the power of C. And since we did Musil over the Sherwood number, we can take that Prindle over the Schmidt to the power of C. Since that's equals 1, we can actually take that C and just remove it. We don't have to be worrying about that. So with that in mind, we're actually going to go ahead and plug these in from what we have up there. So the Prindle number, we said, is the mu over rho times that heat coefficient. This is that concentration coefficient. We're actually going to go ahead and remove these, other than that heat coefficient, concentration coefficient, because they're they're the same thing. We can just cut it out. And so with that, we can actually go ahead and take these two as the Prindle number 1 over that value over 1 over the mass transfer coefficient, or not, the concentration coefficient, and we're going to go ahead and move that up there. So I'm going to go ahead and already rewrite it as mass transfer coefficient over that heat coefficient, heat transfer coefficient. And that helps us, and I know it's kind of far, because we're going to go ahead and rewrite this quickly right now so that you can see that a little bit better. And now we can see these two values are actually going to end up canceling out, which is great. But we can also rewrite that value right there. There's a spider floating right in the middle of my room. So with that, we're actually going to be taking this value and we're actually going to be setting it equal to something else, because we know that this value is equal to that heat coefficient there, all over rho Cp. And so over here, that means that it's going to be 1 over that value there, K over rho Cp, which allows us to move that rho Cp to the top there. And we can go ahead and rewrite this, rewrite it right now here. So rho Cp over K. And I know these are kind of far, but I hope you can still see. We're talking about these values. I'm going to go ahead and erase this as well so that we can see. You know what? I'll even actually go ahead and rewrite it down here so it's easier to see. Now the last variable that we can take out is that constant right there. So with that, I'm going to just go ahead and erase it, just make it a little bit easier. That actually gives us this, which again, all over here, We can see that as 1 over the Lewis number. So we can see that this is our Lewis relation. And what's good about this is we can see that heat transfer coefficient and that mass transfer coefficient, which is very helpful because finding the heat transfer coefficient is a lot easier than finding the mass transfer coefficient. So in real life scenarios, this could be a huge money saver. Instead of having to go through these long, expensive tests, we can just use this equation here, and it'll find the same, or at least a very similar close answer that we need for the problem that we're solving.